Hello, ladies and gentlemen. I'm Daniel Kabinat-Trefo, and I am going to discuss with you this course, Applied Mathematics for Economics. And today we have 13 topics in all, but this morning I'm trying to discuss logarithm and exponential functions, and of course their application in economics. Right, what I intend doing is that we are going to look at, what a log function is, and of course what an exponential function is. Look at the various algebra involved in, working with them. And then I'll go on to my main focus, and that is trying to know how log and expo functions are being used in economics. So if I want to be a little, more specific, we are going to talk about exponential functions, algebra, log functions, the algebra, and then the applications in economics. And here I'm focusing on three main applications. That is compounding interest, discounting, and how we do estimate growth rates from data points. Now, applied mathematics for economics is a very old sort of discipline, and any book will help you. But then I recommend these three readings, which I find very, very important. The first one is Dowling, and then Alpha Chang, and Raymond and Ziegler. They can all be found in the library of the Department of Economics, and I think in the main library of the university. Now, what is an exponential function? I'll start with an exponential function. Now, an exponential function is any function of the form, b raised to the power, let's say x, where we call b the base, okay? And x, it's more or less the variable. And you can see a specific example that I've given there. When you have, let's say, y equals to, half x, or y equals to 2 raised to the power x, these are all examples of, exponential, functions. It pays to talk about, when you discuss any function, talk about the domain and the range of the function. And if we look at all exponential functions, what we see here is that, the domain of an exponential function is the set of all real numbers, right, defined over the range that we have over there. Now, if you go further, I've given you some examples of exponential functions which you can take your time and go through. One thing you need to know is that for an exponential function, the base b, should lie between 0 and 1, right? And when it's between 0 and 1, you can get half an example. When it's greater than, let's say, 1, you can get the example that I've given here. So it's always important to know that you can have the base being greater than 1 or lying within that range. And based upon the value of the b, you are able to know how the function behaves. I would like you to have a look at how this function behaves. For the two situations that I've talked about. And the first one is when the base is between 0 and 1, and when it's more than 1. So in this example that I've given you, the graphs up there, the functions up there is what we have tried to plot. X is the variable that changes, okay? And then we have the function 2 raised to the power x, 3 raised to the power x. So what is here is that you just insert the value of x into the function, you find the corresponding value of y, and the figures is what we have over there. And if we plot this function, we get something like this. What are the important features of this function? One, you have to know that all the function, they cut the point where x is equal to 0, y is equal to 1. This is something you should never ever forget. And when you have, the base being greater than 1, you see the function increasing. Conversely, you see it decreasing. And notice that what is over there is that they never touch the 0 line. They are what we call asymptotic to the 0 line. So this is a function of an exponential function in a situation when it's greater than, the b is greater than 1, and then when the b lies within the interval 0 and 1. You've also talked about the algebra, how to manipulate certain simple exponential functions. And the basic formula that we use is what we have over here. And these things, I'm sure most of you are quite familiar. Those of you who did elective maths, definitely you know how to work with some of these tools, and I wouldn't spend much time on it. There is some example that have been provided down here. And if you see how they've worked out, we've worked them out nicely using the rules in exponential functions, which I believe you can go through yourself. Now you try and enhance on some of these things. All what I want you to do here is to simplify the function that we have here using the rules in exponential functions. Now, I need to also, talk about what we call natural exponential functions. Notice that there is this word e, which you always maybe have come across. When you take the limit as, let's say, n approaches infinity of the function 1 plus 1 over n raised to the power n, you get this value e, which is called, it's a 2.716 something, right? This value, when you have any exponential function, and instead of the base being b, the base turns out to be, e, then we call it natural exponential function. Now, in many cases, we prefer, calling this natural exponential functions, and if you happen to go further, you know the economic implication of this e value. It has got very, very important economic implication, and you may want to know it later. Now, when you grab this function for different values, this is what you get, and I think in the same way as we did earlier, you can put the values that we have over there into the function, find the y, and try to plot it, and you're going to get what we have here. Now, again, let's talk about logarithmic functions. Now, the log of a given number is the number to which that base of the log must be raised in order to obtain that given number. A simple example, notice that when you have h1 and you raise 9 to the power 2, you get what? 81. And we can write this as log 9, log h1 to the base 9 equals 2. So what it means is that what number do you have to raise 9 to in order to get what? 81, right? What number do we have to raise 9 to in order to get 81? And that number is 2. Mathematically, we try to use these symbols, log of x, y, and to represent the relationship between exponential in functions and logarithm functions. They are the same, but there is a relativity between them, and that relativity is what you can see over there. Now, again, we also have to know that when we talk about the base of a log function or the power of a log function is the same as the base of an exponential function. So the relation that we have over here, the last line over there, do hold for log functions. If we want to plot log functions in the same way as we plotted the exponential functions, and here you can see the table that we have over here, right, where we put the value of x into the values of the log functions, and there we do have the graph that we have over here. One important observation here is that for any log function, at the value 0, you have here 1, right? So it turns unlike the exponential functions, and it's also asymptotic to the vertical axis, and then it rises up or decreases depending on the base of the log. Now the base of a log can be any positive or negative number, all right? But sometimes you want to, try to differentiate between a common log and an exponential log. Usually, when we talk about the base being 10, then we talk about, a common logarithmic function. But in situations where we have the base being equal to an exponential, the value y, then we call that one a natural log. And then many books, instead of writing, let's say, log to the base ex, we write ln x. And again, this is seriously applied in economics, and very soon you know the implications of this ln x, which you will meet as we go on. Another thing we may have to discuss, it's about the rules in logarithm. Those of you, again, who did e-maths may have come across these ones, right? The addition, the product rule, the quotient rule, the power rule, the base research rule, and other miscellaneous rules in log functions is what you have on the whiteboard. And I'm asking you to look at these examples. I've tried to solve these ones all what we're doing is that we're using these properties of log functions to resolve the equations that I've given, and you can go through yourself. But further, I would like you to, do some exercises on your own. Now that we do have a good understanding of exponential and log functions, the next thing we have to discuss is that what is the use of all this mathematics? We are economists. Why do we worry ourselves with mathematics? The simple rule is that there are three major things that we use, logarithm and exponential functions, to solve in economics. The first one is interest compounding. Recall that when you go to any bank and you borrow money from the bank, definitely you have to pay interest, isn't it? And the interest that you pay more or less may depend on the interest rate which you agree with the bank. Am I right? So in this simple example that I have here, assuming that you borrow a certain amount, I call it P, from the bank, okay? And the banks are saying their interest rate is, let's say, R. Today I don't know the interest rate, but sometimes if you go to the bank, it can be, 21, 31%, whatever. Now, what happens is that at the end of the year, what you have to do is that you have to give the bank the money that you collected, P, and then you have to add a percentage of the money that depends on R, that is what, PR. So at the end of the first year, you are going to pay A1, which is equal to P plus P multiplied by R, as you see over there. Now, what happens is that assuming you don't pay that money back to the bank, and then you want to still borrow that money for the second year, at the end of the second year, what happens is that you have with the bank, so the bank would have given you P plus PR, okay, that's the principal now, and then you are also going to pay them an amount P plus, PR all multiplied by an R. And that is what you see in the first equation. That is at the end of the second year, this is what you're going to pay. And notice that if you do simple algebra, you are going to get P into bracket 1 plus R raised to the power square. You can go on, take P equals 3, take P equals 4, and then you see that if P is equal to T, that is at any time T, you are going to pay the amount P multiplied by 1 plus R raised to the power T at the end of T years. Now, I did say earlier, or I didn't introduce you to discrete and continuous compoundings. When you go to the bank and you want money from the bank, you have to know whether the interest rate is being calculated on discrete basis or on continuous basis. When you talk about discrete basis, what it means is that the interest is being compounded at the end of a fixed term, let's say a year. So at the end of the year, is being compounded, and every year at the end of the year is being compounded. There are also situations where the interest is being compounded continuously, that is at any time T. Okay? What we have discussed is a situation when the interest is compounded at the end of the year. And that is why you have A at the end of time T, you have the amount that you have to pay the bank being equal to P multiplied by 1 plus R raised to the power T. So here, what I'm saying is that the interest is being compounded at the end of the year. But again, notice that there are situations in which interest will not be compounded, only at the end of the year. It's possible to go for a situation where interest is being compounded, let's say quarterly, or is being compounded every 6 months. In that way, this formula changes, right? In that way, what is happening is that at the end of the year, you are going to, depending upon how the interest is compounded, you are going to pay an amount which is equal to P multiplied by 1 plus, R raised to the R divided by MT, all raised to the power RT. And I'm going to explain this. In this last formula that you see over here, M is the number of times that interest is being compounded. Okay, M is the number of times that interest is being compounded in the year, in course of the year. So if interest is being compounded, let's say quarterly, then it means M is equal to what? 4. If interest is being compounded, every 6 months, then M is going to be what? 2. And if that is the case, then this is the situation, or this is the total amount that you may have to, pay the bank if the interest is compounded, based on a certain number of times in a year. So notice that when you do have interest, or you go and borrow money from the bank, you should know whether the interest is compounded quarterly, monthly, right? In situations where interest is being compounded monthly, for example, it means M is equal to 12, right? And how much you're going to pay to the bank will depend on how, the compoundings are made in a situation where you are dealing with discrete compounding. And it's very important to take all these things into consideration before borrowing from the bank. Further, I try to, solve some examples. In the first example, I've given you your P, your R, and then your T. What you have to do here is that you should be very good in changing your formula. In the formula that I have over there, when we go to this formula that I have over here, you have so many variables. You have P, you have A, you have M, you have T. And notice that in this formula, whenever I give you, you have how many variables? A, P, R, and then T. You have 5 of them, right? A being 1, P being 2, R being 3, M being 4, and then T being 5. So you have sort of 5 variables. Whenever I give you any 4, you should be able to solve the last one. So if I give you P, I give you R, I give you M, I give you T, and then I give you, that is 4, you should be able to find A. And how you find A will depend upon how good you are in terms of, working with change of subject. So the question can be formulated in any direction.